Good morning. Can you see the shared screen okay? So, thought I'd just do a quick demonstration of something that maybe is something you want to do from time to time, uh, concerning moving files off of Schofield and getting them down to your home computer. So it's a two-step process. Going to move some files off Schofield over onto the file space that is what you access when you're on the Linux pool machines. All the machines in the labs and the CS department, all when regardless of which one you log in, you get the same home directory, right? So I'm going to move them off of Schofield onto one of the quote lab machines, and then move them from there down to my home machine. So I'll just quickly demonstrate how I would do that. I have a directory called samples. It has a bunch of sample programs I'll gin up for you. And if I want to load them up to the Canvas pages, I drag them down to my home machine and then I upload them from there. So I'll show you how I would do that. SCP, which is sort of the cousin of the SSH command. And just to make life difficult for you, the P in the 922 in the SCP command is capital as opposed to lowercase in the SSH command. Lovely. So I'm going to do an SCP and then I want to copy this directory samples and all the files in it over to the lab machines. And so I'm going to do a recursive copy of the directory samples, the local directory. And then I'm going to copy it to one of the lab machines. So it doesn't matter which one I pick. My login ID over there at Linux dash 06 or whatever. And where I want to put it over there, the colon at the end says, now I'm going to give you the path within that machine that I am going to. My home directory is, of course, always tilde. So in my home directory, under my home directory, I want to go down to a 247 directory. And then I'm going to put this samples directory and everything in it in there. And then there's already a samples directory over there, but it doesn't matter. So I hit return and it says, oh, I don't know anything about this machine Linux 06. So yeah, that's cool. Put it in the list. And then I give it my password on the lab machines. These are all over there, right? Now to get it down to my home machine, I'm going to use WinSC to go to one of the lab machines. And so here I am on one of the lab machines. It happens to be the same one. It doesn't make any difference which one it is because they all have the same file system. Excuse me. And so I want to position myself here in this 247 directory. And I'm positioned at the 247 directory. So here's that sample stuff I just copied over. So if I right on that and I hit download, and I could download the whole mess, but that might, take a long time sometimes. So I'm just going to go in here and say new and updated files only. So if it's the same timestamp on the file that's already down here. Don't bother downloading it, right? So he's going to look through there and get all the new or updated files, and he's going to download them, and then they'll be in this directory on my local machine at home here. So that's something you might want to do from time to time. And the reverse process is obviously you move them from here up to some lab machine, and then you'd use the SCP command, but you do it backwards here, right? You'd be copying from there, and then you'd put the to directory or whatever as the last thing. So hopefully that gets you going on moving stuff around from Schofield onto the lab machines, from the lab machines down to your home machine, or vice versa, if you ever have a need to do that. Questions? Okay, so we were looking at this bit twiddling masking stuff, and we noticed that if we used a fence of all F's, that's all ones, and we do an AND operation, excuse me, like this, then everything where there's ones with the bit level and is going to come past, fall through the mask, right? And when we put a 0, that's going to mask off those 4 bits down on the end. So this is done all the time in systems level programming, where we're grabbing things out of some device register, and we got to go grab a certain chunk of the thing out of the device register to see what it is, to know how to control the device or something. So these bit twiddling operations are very common in that kind of programming. The anding with the ones is a way, and then putting a 0 is a way to mask something off. If I want to put something in, I can use the OR, the vertical bar. So now I'm going to take that I3 thing where we masked the F off on the right, and I'm going to OR it with I4. And you'll notice I4 has all zeros and then a 5 in that position. So when you're ORing, if you don't want to modify this part, you put zeros, right? And when you want to modify that part to put it in, you put something there. So let's just compile it, run this thing. Alt X, compile. Yeah, that's the command I want. And then want to run it. Alt exclamation point to give a shell command, and the command I want is that. So now you see that we masked off the F, right? Right there. This F here got masked off with the and then when we ORed it, we put the 5 in there, right? So we got rid of that part, and then we shoved that into that byte. So this is a way we can move any of these bits, twiddle the bits, you know. Any questions about this masking kind of concept? So this is part of what you're doing, I think, in the second homework problem, is pretty much just this kind of masking, bit twiddling stuff. And to some a large extent, also the third problem, you're doing a bunch of masking, but you're also shifting things around, which we'll cover today. So let's just get into the lecture then. No questions about this masking concept? The first homework problem is really understand what a pointer is and how to reach into memory and pull a byte out of memory. So we looked yesterday at doing addition on the computer, both of unsigned values and signed values. And we noted that the addition that we do on the computer is not really the same as adding integers in the mathematical sense, right? Because we have this limited amount of precision. And if we add two W bit wide numbers together, it's possible we would need W plus 1 bits to hold the true result, but the registers don't magically grow in size on the computer. So it's a sort of a mod function going on there. You do the true result mod 2 to the W, you're truncating off the any overflow that carried out from the operation. So we have to constantly bear that in mind, and that's of course why we have all these different size things, a byte, 2 bytes, 4 bytes, 8 bytes, all these different size numbers that we can play with because we size them, the variable type, to match the range of values that we're dealing with for some specific case. So you have to constantly be aware of the limitations of the sizes of these things on the computer. There are, of course, software implementations of arbitrary precision arithmetic packages, which can do the make the thing bigger and bigger and bigger, to hold whatever it needs to hold. But those are very slow compared to the opcodes doing the operations on the computer. But those libraries are available if you have a need for that sort of thing. The ranges uh, that we looked at were dependent upon whether we were doing unsigned or two's complement representations. You get one less bit of magnitude in the two's complement representation, so it's half the range of the other one. So if we go to looking at multiplication, the same sort of thing happens, only much worse. With the addition, we would need one more bit to hold the true result. Well, with multiplication, we would actually need twice as many bits to hold all the possible values we could generate out of multiplication. So obviously that's not going to happen, and we're going to have much more opportunity for overflows and underflows and those sorts of things when we're doing multiplication operations. So if we look at an unsigned value and contemplate doing multiplication, an unsigned value is always greater than or equal to 0, right? It doesn't represent negatives, it just represents magnitudes. And if we multiply two unsigned values together, the result will always therefore be greater than or equal to 0. But it'll be less than or equal to what? Well, it would be 2 to the w minus 1 would be the biggest number we could possibly put in w bits as an unsigned. And so the range of possible results would be 2 to the w minus 1 squared. So let's look at some interesting properties of binary numbers quickly. Just notice some interesting properties here. And get over to the buffer I want. Okay, there's my blackboard. So if we just look at 4 bits, I put ones in all those positions. This represents what? 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? So if I have 4 bits, the biggest number I can put in there is 15. Well, what is 15? Well, 2 to the 4th, the number of bits I have, would be if I had a 1 in this to the left there in the 5th position, right? That would represent the weight 2 to the 4th. So having 2 to the 4th would be 16. And the interesting property I want you to think about is that if you put ones in all these positions, that value is 1 less than just having a 1 in the next position to the left. Think about if I added 1 into this. I get a 0 carry, 0 carry, 0 carry, 0 carry. So I'd have 16 would be a 1 and then 4 zeros, right? So 4 1 bits is one less than having a 1 in the next position. So 2 to the fourth, 16. This is 2 to the fourth minus 1, which is where that's coming from. If I have W bits wide, then I get 2 to the W minus 1 is the biggest thing I can represent in W bits. And if I have two of those to multiply, then the biggest number I could possibly generate would be 2 to the W minus 1 squared, which if you do your ninth grade algebra and multiply it out is this thing, but who cares? It's just, is expressing the concept better than looking at that rot. So does everybody see where we get this range of the true values would occupy that range, right? Well, in order to store that, how many bits would we need? For the biggest thing we could possibly generate. We would need up to twice as many bits to store the true result, right? And it's similar, but off by 1 bit when you do the twos complement because the magnitudes only take up, you know, the one less position. Excuse me. So there, the twos complement min that we have, right, of multiplying two things would be in this range, and our twos complement max multiplying two things would be in this range is one less bit that we have to play with as opposed to up here. So still, we're in the same box. We'd need up to 2W bits for that largest negative value we could possibly create. So the picture is, of course, you take 2W bit wide things, multiply them, and the true result would take this many bits. But we don't have that many bits. We just have the number that we started out with. It's where it's going to put the result. And so the unsigned multiply in W bits of U and V would be the true thing, would be this, and then we truncate it to the W bits that we have, right? So we just ignore anything that carried out into those positions when you did the multiply. So it's as if you're doing the true result, U times V, mod 2 to the W. 2 to the W is this bit just to the left there, right? So you're truncating it off at 2 to the W. Everybody all right with this? Okay. So if we do signed multiplication as opposed to unsigned, we get a real similar thing. We're going to need still twice as many bits, but it's going to ignore all this stuff over here. So it's the same kind of thing going on there. Now we want to look at the concept of simulating multiplication with a shift operation. We've already run into this shifting thing a little. The shift operators in C are these double guys. Double less than is a shift left. Double greater than is a shift right. We'll look at each one of them. If I have an U and I want to shift it left K bits, that's as if I multiplied U by 2 to the K, right? Well, let's look at some stuff. If I had a decimal number, 7, and I shifted it left and put a 0 behind it, well, that multiplied it times the base of the number system. I multiplied it by 10. If I shifted it again, I multiplied it by 10 again, right? Well, it's the same thing in binary. If I have a 1 and I shift it left one position, that's 4 in binary, right? So I multiplied it by 2. If I shifted another position left, I'm sorry, that's 2. This is 4. 4, so I got 1 times 2 is 2 times 2 is 4. So shifting left and pumping a 0 in any number system is multiplying by the base of the number system, right? So in our binary guy here, if we shift it left k positions, you're multiplying by 2 to the k, right? So if I start off with some some number, and then I shift all the bits to the left, right? I've multiplied by 2 to the k, but the ones on the left over here that don't fit jump off into the bit bucket, right? So it's more like this mod thing again, right? As long as you don't have any significant 1 bits just leaping off the cliff here, you're getting a true multiplied by 2, a power of 2. Once you get somebody jumping off the cliff here, the mod thing comes into effect, right? So you shifted left 3 bits is the same thing as multiplying by 8. Shifted right 5 bits, subtract, shift right 3 bits. This would be 2 to the 5th you multiplied by. This would be 2 to the 3rd that you multiplied by. So the result is multiplying by 24. 32 minus 8, right? So we can do multiplications of powers of 2 and sums and differences of powers of 2 by doing shift operations. Well, why do we care that we can do that with shift operations? Well, the most expensive in terms of the number of clock cycles that it takes instructions on the computer are floating point multiplication and division is the worst. And a similar thing happens with integer, which is what we're dealing with. Integer multiplication and division take many, like 4 clock cycles or something. You can do a shift operation in 1 clock cycle. So we're always looking in the computing world for how to make things faster. And so if we can get the effect of multiplying by a power of 2 by a 1 clock cycle shift instruction, we might prefer that over actually running the stuff through the circuitry that does the actual multiply instruction. Well, somebody has a question here. What does multiplying bits look like? Do you have to perform the multiplication in decimal and hex, convert to binary, or well, that's what the circuitry is for, right? It does the multiply all in binary. If you want to work it out on the back of an envelope, whatever works for you is okay. You could do it in binary. They didn't teach you that in the 2nd grade. They taught you how to do it in decimal, but you know, you can do it directly in binary. But the computer, everything happens in binary, right? It's not going to convert anything to some decimal representation and do the thing. The circuitry is built to do it in binary, right? Does that answer your question? So we have this little example here, and this is one of these crazy pedantic examples. No one in their right mind would ever write a function to do this. If you wanted what this function does is you hand it something and it multiplies it by 12 and hands it back to you. Well, we'll learn in this course all the overhead associated with making a function call and getting those parameters and everything and putting the result back to the caller. So you wouldn't do that, unless you were insane. You would just write x times 12 whenever you wanted multiplied by 12. But for the purposes of this pedantic example, we want to have this little function that you hand it something and multiplies it by 12 and gives you the result. And we look at what came out of the compiler when we compiled this. And this is a possible outcome that you could have gotten when you compiled this code down to this assembly language. And so we want to look at what the assembly language is actually doing to do this multiply by 12 thing. The first thing we see here is this load effective address long word instruction. That's the assembly language instruction. And the purpose of this load effective address long word thing really, as you'll learn later, has to do with how we have a operation on the computer that sort of mimics exactly what you want when you're subscripting into an array to get the right address. But we're not using it for that purpose in this example here. The way this load effective address long word instruction, and you'll learn that the last letter of assembly language instructions most times tells you the size of the operands that you're operating on. And a long word is 32 bits. The Intel processors started out being 16-bit processors. And so a word was 16 bits. So when they made the 32-bit processors, they said, oh, well, we'll call those long words, right? When they got to the 64-bit processor, they call them quad words, 64 bits, right? So the L here means long word or 32 bits, which is the size of this EAX register. In assembly language, we have names for the registers. And then when we write it in assembly language, we put this percent sign in front of it to say, this is a register name I'm talking about here. So this says, got three things to this LEAL instruction. What it does is it takes the one in the middle here and it multiplies it by the third one. And then it adds that to the first one. So we got 2 times EAX added to EAX, which is effectively multiplying EAX by 3 is all we're trying to accomplish here. Now, it really doesn't do a multiply instruction here with the 2. This thing on the third part of the LEAL instruction is always a power of 2. So what's really going to happen is it's going to take the EAX and shift it left 1 bit position to give you the effect of multiplying by 2. And then it's going to add to that. So all that accomplished was taking whatever was in the EAX register, which was hopefully this X thing, right? And multiplying it by 3 and leaving it in the EAX register. The next instruction is a shift arithmetic left long word instruction. And whenever you have a $sign in assembly language, that means this is a numeric literal. It's the number 2, right? So I want to do a shift arithmetic left long word 2-bit positions of EAX. Well, that's effectively going to multiply what's in there by 4. So I've multiplied by 3, then I multiplied by 4. So I got the thing multiplied by 12, but I never took the thing and ran it into the multiplication circuitry in the processor. And the idea being I can do these 2 instructions in 2 clock cycles, probably, maybe. And maybe the multiplication instruction, I had to look it up. Maybe it takes 4 clock cycles to do the actual multiplication instruction. So I'm sort of simulating doing this multiplying by 12, but I'm never really actually using the operation code on the computer to do an actual multiply, right? Now, the downside of this kind of crud, this is what we call a compiler optimization. Compilers have all sorts of little tricky optimizations they can do. Though, if you ever take a compiler class, you'll learn that this flavor of compiler optimization belongs to a class of optimizations known as reduction in strength. Getting the effect of a more expensive instruction using a cheaper instruction in terms of the number of clock cycles it requires to do it. So this is a compiler reduction in strength optimization. The downside is that the LEAL instruction and the shift instructions don't light up the condition code bits in the event that we would have had overflow. If you use the actual real multiply instruction, there's those condition code bits we've alluded to before. And a side effect of doing the multiply instruction is if it overflowed or underflowed in the case of the two's complement stuff, this bit would get turned on in that condition code stuff. And then you could go look at that condition code and see if you had overflow. You could do that in assembly language. But those bits don't get lit up by doing the cheating version of the multiplication here. So you're kind of playing fast and loose and thinking, well, this is not going to overflow, or if it overflows, I'm not going to need to worry about it or whatever. So that's the sort of thing you're kind of giving up by doing it this way. So as we go through, we're going to be looking at tons of C code and what comes out of the compiler to implement the C code. And so you'll not always see some straightforward, oh, there's a multiply instruction somewhere. Well, not necessarily. Does everybody understand this example? All right. So if I wanted to do shifting left does the multiply, right? So if I shift things right, that's like dividing by powers of 2. So take something and the shift right in C is 2 greater than sign. That gives me the floor function of u divided by 2 to the k. So what is this floor function? Some of you may not have run into that in your math studies up to this point. So if you go to the course web pages, get that up here. Course web pages, and you go to the announcements of all places. I probably need to put it somewhere better. And you scroll down through these announcements, you'll find this little thing here that says definition of the floor and ceiling functions. So if we had some number like 2.4 and we took the floor function of it, that's just saying, give me the integer that is just below or equal to the value that I put in. So 2 would be the floor. Ceiling is his opposite, right? 2.4 ceiling would give you the integer that lives up above there. So that's 3. If you have 2, then floor and ceiling are 2, right? So you see it's just kind of moving it down to the integer below it or moving it up to the integer above it. So that's our floor and ceiling functions. So when you do this shift right business to do a simulated divide, it's as if you're getting the integer that's just below the real result of u over 2 to the k. In other words, there is no fractional part. The fractional part fell off into the bit bucket on the right when we did the shift. Does that make sense? So if we do unsigned power 2 divide, we get what's called a logical shift right. And that means that we're pumping zeros in on the left side. As we move things over, zeros get pumped in to fill the vacated positions on the left. That's a logical shift. And that's what would be generated by the compiler if you wrote a C statement that did a shift right of an unsigned variable. You'd generate a shift right logical. Okay. And what the result would be is like if our favorite number 15213 was sitting in there, which is this bit pattern over here. If we shifted it right 1 bit, well, that zero, that one rather, is going to jump off the cliff into the bit bucket, and this zero is going to move over to take his place on the right. So everybody moved over one position, and a zero got crammed in on the left. So you have three zeros instead of two. So that's the shift right logical. Shift it four positions, the same sort of thing. The rightmost four guys jump off the cliff, and then everybody comes over and we fill it with four zeros before the stuff that we had originally. Shifted eight would be that, right? So this is simulating divide by 2, divide by 16, divide by 256, right? And so the actual numbers that you end up with in decimal look like these guys. The true result, including the fraction of doing a division by 2 or 16 or whatever, right, would have these little fractional parts in there, right? If I divided it by 2, that one bit hopped over to the right of a binary point that would be sitting there, right? So he was representing 1/2, 2 to the minus 1, right? Just like all positional notations, when you have a decimal point, well, this is a binary point, so it's 2 to the minus 1, 2 to the minus 2. Those positions have those weights, right? So like if we did the real division, he should have a 1/2 in the result. Well, we're doing integer stuff with unsigned integers. And so the result is going to be an unsigned integer. It doesn't magically turn into a floating point representation, which we'll talk about what those look like later. So this little fractional part in the real result fell off the wagon, right, into the bit bucket there. So it's as if this floor function was applied to the real result. That's what that's trying to say, right? Give me the integer that lives just below whatever this actual real result is, if it doesn't work out to be an integer. Is everybody cool with this concept? So that's what's going on with simulating division to the right. And you'll notice that in the case of the unsigned, since it's lopping these things off, it's doing what we call round towards zero, right? By just chucking the thing away, it's making this thing round down towards zero. So if we simulated the x over 8 with a shift right logical, because it's an unsigned variable, the logical means pump in the zeros from the left, 3 positions, that would simulate our divide by 8. But it's doing a round towards 0. So now if we look at signed whose complement things that take on both positive and negative values possibly, and we're trying to simulate division by a power of 2 with a shift right operator, you get the same kind of thing. You get x over 2 to the k, and you get the floor function, the integer just below the true result, right? And then rather than doing a logical shift when we're dealing with 2's complement values, we do what's called an arithmetic shift. We've already seen something similar to this when we took a short and put it into an int. If the short was negative, remember we had to do that sign propagation stuff, filling the sign bits all the way to the left to get the right value and the bigger encoding. Well, it's the same kind of thing going on here. If we start out with a negative number as a 1 in the leftmost position and we shift it right one position, we have to pump in a 1, not a 0 from the left till we get the correct value, right? So when we do shift rights of signed entities like ints, not unsigned ints. The instruction generated by the compiler is a shift right arithmetic operator, not a shift right logical. And so, what's going on with the rounding here when we're doing these shifts of signed entities shifting to the right? Well, if it had a positive value in it and we shifted it over and the zeros propagated because it's propagating the sign bit, right? Whatever was sitting in this position gets propagated into the vacated positions, right? The sign bit. If a thing was positive to start out with, well, it would lop the thing off, and that would effectively be rounding towards zero, which is what we want. But in the case of a negative one, right, when you lop off this zero point 0.5 that jumped into the bit bucket, you're actually rounding away from zero, right? You're making it more negative than the actual true result should be. So to be truly consistent, we need to cause it to round toward zero to truly simulate what the result of the integer division should have looked like, right? So to get the round towards zero, in the case of if you started out with a negative number, you want the ceiling function of the true result there, right? To round towards zero. So how do we get that? Well, the trick is before you do the shift, you add a bias of all ones in. If I'm going to shift k positions, I take k minus 1 positions over here, put all ones in it, and add that to the thing. And then if that would have caused a carry to happen over here, I've sort of preloaded what the rounding should look like to round towards zero. And then I do my shift and throw the things off in the bit bucket, right? So the bias, adding this bias in, gives me the effect of the ceiling function or rounding towards zero when I started out with a negative value to begin with. Does everybody see the trick there? Questions about this? All perfectly clear? All right. So if we had um, some bits up here in these k minus 1 positions where when I added the ones into it, it would cause that to pop a 1 over there, right? Then when we shift the thing over and throw these away, right, that 1 effectively is our rounding up towards zero that we wanted the effect of, right? So it's only ever going to affect this last bit that shows up after you do the shift, right? The incremented by 1, this guy ends up over here, right? You see how to do the biasing to get the rounding to work properly to simulate division by a power of 2 of a signed entity. So we have to do the shift right arithmetic, not the shift right logical. Shift right logical always pumps in zeros. Shift right arithmetic for the signed guys propagates the sign bit. But we also have to look and see if the thing we start out with is negative, in which case we need to add the bias in before we do the shift. If it started out positive, we don't need to add the bias in. Just lopping off the stuff rounds it down towards zero, right? Pretty slippery, huh? So now to actually see how we could truly simulate division of these signed quantities using the shift operator, we would have some code like this perhaps. The test long word instruction is, you'll learn a lot more about test instructions later. It's just executing this instruction for the side effect of lighting up some of those condition code bits. And so what we want to light up in the condition code bits is a bit that says whether the thing that we just did the test instruction on was negative. It would light up this one particular bit in those condition codes. Then we do a jump signed, right? If the sign bit is flipped on in the condition code bits, we do this jump. Otherwise, we don't. And we jump to label 4. A label in assembly language looks like a something with a colon after it that we stick on the left side of the page by convention. So if this thing is negative, the jump will happen and we'll go here. And then it's going to add 7, right? 1, 1, 1, 3 positions because we're going to shift right 3 positions to do the divide by 8. So that's adding in that bias to the value, and it jumps back up to L3. If the thing was positive, we just fall into the L3. If it was negative, we did the little fix up with the bias and then came back here. And the shift right arithmetic long word of 3-bit positions on that simulates the divide by 8. And then this is the assembly language for a returning from a function. To give the value back from the function, this int that we're giving back, we always leave the return value in the Intel processors in the EAX register. So our result, this x over 8, is sitting in the EAX register, and that's this integer that gets returned back. So do you see how this code properly simulates the divide by 8 for a signed quantity, an integer, not an unsigned, right? We have to account for the fact that, oh, if the thing started out negative, we got to add the bias in to get the round towards 0 to work right. Then we can do the shift and then we are good. Questions about this little chunk of code? Now, it could be that if you look at all this nonsense that's going on, it might be just as cheap to go ahead and do an actual divide instruction and, however many cycles that takes as opposed to all this sort of nonsense, because the divide instruction does all that rounding junk for you, properly. So this may or may not come out of the compiler when you see this. He may have just generated a integer IDIV integer divide instruction. Okay, so the rules of the game. When we did addition, we saw that unsigned and signed, pretty much is just think of it in terms of a mod function where you're lopping off some stuff. Multiplication, same sort of thing, only now it's mod. Truncating, the probability of something getting truncated has gone up significantly, right? Because we need twice as many bits rather than the number of bits we started out plus 1. So in any event, hopefully that makes sense. And then the rules are a left shift where you're multiplying doesn't make any difference whether you're using signed or unsigned things. You're just pumping in zeros from the right. On the computer, there actually are 2 different instructions. Actually, I should rephrase that. In the assembly language, there actually are 2 different mnemonics. One that says shift left logical, shift left arithmetic, but it's kind of stupid because they do the same thing. They pump in zeros from the right side. One of these days, I'm going to assemble a little chunk of code with the two different ones in it and see if it actually is generating the actual same opcode on the computer. Because I think there's only one opcode, but there's two assembly language mnemonics to get you the same opcode. So it doesn't make any difference in the case of left shifting, right? You pump in zeros from the right. But when you're doing right shifting, because of this negative versus positive thing, you got to do the sign bit propagation when you do shift arithmetic, right, to simulate what should happen for the signed quantities. For the unsigned ones, you do shift right logical and pump in zeros from the left. So there are two distinct shifts for the right shift, the logical versus the arithmetic. And then to deal with the rounding towards zero thing, we have to add the bias in to fix the fact that if you just lopped it off, you're rounding the negative results away from zero, which is not what you want. You want both the positive and the negatives to round towards zero. Everybody cool with that? Okay. Well, I have office hours at 2 o'clock today, 2 to 3. You can drop in. We can talk about inspiration for the homework. We can talk about any of these bit twiddling examples, any of the material that we've gone over, whatever you want. So, are there any questions before we wrap up today? If not, then I will either see you at office hours or tomorrow to wrap up our second week. It's hard to believe that we have made it through 2 weeks already. So I will see you later then. Have a great day.